Hello. Today we're going to look at some applications of DeMoirvres theorem, and we're going to start off by looking at something that I can throw at you that's a little bit of a trick, a little bit of a catch that we need to watch out for. So if I'm asked to get z to the power of 5, where z is cos of 45 minus I sine of 45, immediately this looks like something I can just use DeMoirvres theorem for, but there's a problem because of this minus. So if we get a minus in between our cos and our I sine terms, how are we going to resolve this? Well, the way that we resolve this is, as it so often is, to draw a picture and see if we can put this number in context. Can we write this in a form that allows us to use DeMoirvres theorem? So if I draw a sketch of this situation, now if I have cos 45, that's going to be 1 all over root 2. And sine of 45 is the same thing. It's 1 all over root 2. So I have my z that I have to the power of 5 would be 1 all over root 2 minus 1 all over root 2i. And once I do that, it becomes fairly obvious what's going to happen. I am going to be able to draw a sketch of this and figure out what the equivalent angle would be for this number, writing my plus in here. So I'm effectively going to turn this number into polar form, and my problem will be resolved in standard polar form. I just put it to the power of 5. I can use DeMoirvres theorem. So what does this number look like? Well, it's plus in the real and minus the same thing in the imaginary. So I end up down here. So the angle I am looking for is going to be that angle there. I'm starting at the positive real axis, going anti-clockwise all the way around to where my number is pointing. And now I just need to figure out what that angle is going to be. So if I have gone around to here, I am in the fourth quadrant. And I can have my model triangle. I already know I'm going to get 45 degrees from this because of the fact that it's given to me directly. But just to reinforce what we would usually do, we have our model triangle and we get our alpha of 1 over root 2 and 1 over root 2. I already know the modulus is 1 because there is no number in front of here, so we haven't bothered to write in the modulus because it's just 1. So I already know the modulus of my number. So my angle is going to be tan of alpha is going to be 1 all over root 2 all over 1 over root 2. Going to be 1, and I know that that means that alpha is going to be 45 degrees. Again, I can simply read that from in here. This is just to reinforce it. If we were unsure in an exam situation, we can very easily and quickly check that we are correct in the same way as we usually would. So now I have my reference angle. I look at what quadrant I'm in. Well, this little angle in here is my alpha, is my 45 degrees. Should have had my triangle the other way up. And then if I subtract that away from 360 degrees, that will give me my angle that I am looking for. So in quadrant 4, my theta is going to be 360 minus 45 is 315 degrees. So now I am able to rewrite this number that I started out with as cos of 315 plus I sine of 315 all to the power of 5. And now I'm where I want to be. I'm able to use DeMoirvres theorem. If I wanted to, I could write in my radius. So if we like, we can write in that our radius is 1. And then when we use DeMoirvres theorem, which we have on page 20 in our log tables, I've written it in here, we're then able to have 1 to the power of 5 1 to the power of 5 cos of 5 times 315 plus I sine 315. Sorry, 5 times 315. Which ends up being equal to 1 to the power of 5 is still just 1. And I end up with cos of 1575 plus I sine of 1575. Again, I have dropped the 1 because 1 by this is exactly the same thing, so you don't need to bother writing it in. I put this into my calculator, making sure that my calculator is working in degrees, and I end up with minus 1 all over root 2 plus 1 all over root 2i. So all I have done is rotate around. Obviously, this is way more than one rotation, but all I'm doing, because I have a modulus of 1, is I'm just circling around my origin point over and over and over again. And if z was greater than 1, I'd be spiraling out as I got larger powers, or if I had powers between 0 and 1, fractional powers, I'd be spiraling inward. Now, let's have a look at another application of this. Now, this is if we're asked to show that cos or sine of multiple angles, so 3 theta or 2 theta or 5 theta, something like that, are equal to a particular number of cosines or sines added together or subtracted from each other. So effectively, this is an identity type question. And you could be asked to say cos 3 theta in terms of cos theta or in terms of sine theta. Doesn't matter. What we have to recognize is that for some of the smaller ones, for instance, the question that I have here, it would be just as valid to use trigonometric identities. So the identities that we have on page 14 and 15 in our log tables, we would be able to use them. For instance, in this case, we could break cos 3 theta up into cos of theta plus 2 theta. We have a rule for that on page 14 and 15, and then we could use the rule for cos 2 theta to break it down further, and we'd be able to use identities to get this relationship out. But it can be faster, particularly if they give you a larger number. So if they ask you cos of 4 theta or something like that, it becomes quicker to try and use DeMoirvres' theorem in consort with the binomial expansion, both of them on page 20 in your log tables, to get these relationships. And we're going to look at how we do that now. But again, if you see a question like this, you are perfectly entitled to use trigonometric identities on page 14 and 15 in your log tables, but we can also use this method of combining DeMoirvres with the binomial expansion formula on page 20 in our log tables. So if I have cos 3 theta, well, I know that the DeMoirvres theorem, if I have 3 theta, that means I would have originally had a complex number to the power of 3. So what I can say, if I have 3 theta that I'm asked about, I'm going to be cubing a complex number. So what I am going to do is say that I have some z, which is equal to, I'm just going to have a modulus of 1, a radius of 1, theta plus I sine theta. Again, I have a modulus of 1, so I don't bother writing it in. And then if I had z cubed, what are the different ways that I could write that? Well, I'd have my cos theta plus I sine theta in a bracket all cubed. That's definitive. If I used DeMoirvres' theorem, I'd immediately be able to write down that that would be 1 cubed, which we won't bother writing down this time, 3 theta plus I sine 3 theta, which is nice. Again, we'd have 1 cubed times this from DeMoirvres' theorem, but this is also 2 terms in a bracket to a power. So I could use the binomial expansion to multiply this out. I could also just multiply these brackets out. You will get the right answer, but it starts to get extraordinarily messy. Even the binomial expansion gets quite messy. So what we're going to do is multiply this out using the binomial expansion on page 20 in our log tables. Page 20 in our log tables for both of these things. So we're going to take this and we're going to use our binomial expansion. So we have, I'm going to write out the formula for you and come back to you. Now, I have applied my binomial expansion. So I have my first term to the power of 3. I have 3, choose 0, and first term to the power of 3. And then my powers on my first term are dropping to 0 there. And my powers on my second term, which we must be very careful, is I sine theta. I is in my second bracket. So it's going to get squared here. It's going to get cubed here. If I drop the I will get entirely the wrong answer from this method. So I must be very careful. I sine theta is the second term. All of that together is the second term. So now we're going to start multiplying this out and see what simplifications we can make. So having multiplied this out, I have 3 choose 0 is just 1, and I end up with cos cubed. And what I have done is taken my coefficient, so I have the 3 here from the 3 choose 1, and I have the I to the power of 1. So I have my coefficients written out in front, and then my trig terms, which is how I would always write out trig work like this, where I have my coefficients out in front, and then my sines and cosines multiplied together afterwards. And here I am careful that I have I squared as a coefficient, and here I have I cubed as a coefficient. So this part I recognize is going to be minus 1. I squared is minus 1, and I cubed, following the same logic, is going to be minus I. So now I'm going to end up with some imaginary terms and some real terms, and now I'm going to be able to equate imaginary with imaginary and real with real from my DeMoirvres theorem solution to this problem. So having multiplied out my i's, the only thing that I've done here is do these substitutions that I talked about. I now have this is real, and this is real, this is imaginary, and this is imaginary. And this is all equal to my DeMoirvres theorem. This is two different ways of multiplying out this bracket, one using DeMoirvres theorem, the other way using binomial expansion, but they're equivalent. So this real part must be equal to these real parts. This imaginary part must be equal to these imaginary parts, because they are exactly the same thing. They're multiplying out brackets using two different methods. They must be real with real and imaginary with imaginary. Now, which one do I want in this case? I want to isolate cos theta across 3 theta, so I want to get the real part of this. If I was asked about sine 3 theta, I would be getting the imaginary parts equal to each other. But here, I want the real parts. So I'm going to now have this new equation and see if I can simplify it down to what I was asked for. So having equated my real terms with my real terms, I now have an equation that only involves my cosines, and my now I need it to only involve my cosines, but I have this sine squared. So I think back to my work with trigonometry, and I know that sine squared would be equal to 1 minus cosine squared, because one of our most important relationships is cosine squared plus sine squared of the same angle is equal to 1. So we can use this substitution to get everything in terms of cosines and simplify down to what I'm asked for. So now I use this substitution, a very common substitution from page 13 in our log tables, and I have substituted in my 1 minus cosine squared. I multiply out this bracket, and then I add like terms. Sorry, that should be cubed. And what I end up with is what I was asked for. And I recognize this by simply playing through my